checks real quick.
Testing.
Please begin.
Okay. So I'm Jesse Luers. I'm from Infinity Interactive, and I'm giving this talk is about Rust. Rust is a new systems language being developed by Mozilla Research. It's still in development, but they're planning on having an initial stable release later this year. This talk, they've made a bunch of development releases over the past year or two. This talk is actually going to be based on the current state of Masterix. They've been making a lot of, there's still been a lot of changes. And so if you're running on the latest development release, the examples might not work, but that's just why. So Rust's goal is to provide an alternative for projects which would otherwise be written in C or C++. The problem with C-based languages is that they're very difficult to use correctly as your project gets larger. It's very easy to accidentally write code that causes seg faults, accessing memory that doesn't exist, memory corruption, data races, that sort of thing. There's not really any protection in the language for those kind of issues. And these are very important because they can cause security issues, data loss, and things along those lines. The reason that people still use C++ is because it gives you a lot of control over the code that you write. It allows you to write code that wouldn't be possible in other languages. Like there's not really a way to write, say, like an interrupt handler in pure Perl. Like that's not. You need something that can actually access the underlying hardware. It also allows you to write very efficient code. Like if you're writing computation-heavy code, writing it in C++ can make it several orders of magnitude faster, and that's why there's a lot of excess modules on CPAN with the purpose of speeding up performance critical code. In the Perl community, we often talk about premature optimization and how getting that last 10 to 15% of performance out of a piece of code usually isn't worth it. That's really a factor of the kinds of applications that we write. We can ignore a lot of those kind of things because of how insignificant they are compared to the time that it takes, say, the OS to read data from disk or to pull data from a database. But when you're actually writing like a disk controller or the actual database itself, that 10 to 15% does actually matter. And so that's the kind of applications that Rust is trying to target. And so the Rust goal is to provide that same level of control that you get from C++ while removing as many of the dangerous sharp edges as possible. Its philosophy is based on the idea of zero-cost abstractions. One of the main benefits of writing in C++ is that it's very easy to see, given an example of C++ code, how it actually maps to how it's actually going to be executed, basically. And for Rust to really be a replacement, it needs to retain that. That means you can't, it's not going to have things like mandatory garbage collection, mandatory boxing of variables where every variable needs to be allocated in a certain way. Really just no actual runtime at all. It has a standard library, but it's not actually required in much the same way in C or C++. You don't actually have to have the standard library available to be able to run code. Rust has the ability to do these things, to provide boxed variables, to provide reference counting and garbage collection, but they're all optional. And so for most code, you don't have to actually use them if it's actually not appropriate for what you're doing. And even for new abstractions that it introduces, things like closures, it's built on enough of a foundation where those can be inlined away so that the code that actually ends up being generated doesn't need to be any slower than the code that you would write with normal pointer manipulation in C. So basically, the compiler can do all these checks at compile time to eliminate things like null pointer accesses and memory corruption and data races, ideally without adding any actual overhead. The checks should all be able to be done at compile time. Sometimes avoiding those kind of issues isn't always possible. Like you still have to be able to access the underlying hardware. You still, like, Rust is self-hosting. The compiler is written in Rust, and so you need to be able to access. You need to be able to write the primitives that are necessary for that to work, and also. The compiler is only ever going to be so smart, and sometimes you kind of have to tell the compiler to just trust me, what I'm doing is actually okay, in order to make code that actually works well and runs quickly. And so Rust also provides a way to bypass those safety checks in certain limited scopes, in order to accommodate those kind of needs. So a common question at this point is why is this require a new language? Like, can't you just write, like, couldn't this be like modified from C++ to like get something that actually accomplishes this? And the answer here is that doing this in a way that actually accomplishes all of the safety goals that Rust is targeting. No C++ programs in existence, no non-trivial C++ programs in existence would compile under those kind of restrictions. You need to be able to annotate the code with reasons why this is safe, basically. And at that point, you're already basically you're on your way to a new language at that point anyway. And Rust is based on LLVM, which is the same backend that the Clang compiler uses. So it's not like it's starting from scratch either. Most of the optimizations that LLVM provides, or that you get when you're using Clang, which is the default compiler on OS X, those optimizations are mostly done on the back end after the language has been parsed. So Rust can share in all of that work that's been done. So it's not throwing away all that work. Another question is why is Mozilla in particular doing this? And so the reason behind this is that there are a lot of areas that are still performance critical, and these days browsers are really one of them. If you really kind of stand back and squint a little bit, browsers are kind of becoming an OS level kind of abstraction. You have all this untrusted code that you're running all the time that needs to be safely sandboxed. It needs to run quickly and has to be able to access things like OpenGL and microphones and all this kind of hardware. And so you basically you run into a lot of the same issues there. And at the moment, Firefox is around 8 million lines of C++ code. And you pretty much can't write 8 million lines of C++ code without there being some serious security issues in there somewhere, or data corruption or things like that. And these kinds of bugs, memory corruption and concurrency, data races kind of things, are the kinds of bugs that you can't really write tests for because they only show up in very specific circumstances. These are the kinds of things that you really need to be able to verify at compile time to make sure that this is actually not possible to happen. So with that in mind, Mozilla is developing Rust in order to they're at the same time working on a new browser engine called Servo, which is using Rust's stronger safety guarantees and the stronger parallelism support that Rust also includes to kind of work on the next generation of browser engines. It's also still a work in progress, but they also are hoping to have not necessarily a browser for the public to use, but something that's actually usable, like a proof of concept, basically by the end of the year. The rendering engine already passes ACID 2, and it does a lot of parallelism and that sort of thing. So that's kind of where this is going. For the language itself, Rust has syntax based on kind of C and ML, this is a hello world. You declare functions with fn there. Main is the entry point to the program, and print line is how you do is basically the same as printf. There's some differences, but here is a more complicated example. This is actually from the main page of the Rust website. You can see variables being declared with let. Variables are they have to be initialized at the point of declaration. You can't have uninitialized variables. They're immutable by default. You can see underneath there, let mute is declaring a mutable variable. You have to actually declare that. Iteration through a for loop. There's also while loops. In this example, you have the chars method on the string program, which returns an iterator, which iterates through all the characters in the string. Characters are 4-byte Unicode code points. Strings are UTF-8. Another minor thing you might know is that for loops and as well conditionals and while loops don't require parentheses, similar to Perl 6. That's just a syntax thing. Rust also has pattern matching, like OCaml. You can match on arbitrary data structures. This one is just matching on a character, but you can match on arbitrary data structures. The compiler actually verifies that your match is exhaustive, so that you actually have to handle every case explicitly. And so that provides more guarantees that you're not, like especially during refactoring, if you're matching against, say, an enum, and you want to make sure that you're actually covering everything if it changes. And finally, you can see a more complicated example of print line at the end here. The syntax for this is actually based on Python. The curly braces there, the empty braces basically mean to just print out the variable that's given. However, it should default to be printed out. You can also have arguments in there to, like printf has, to print it out in different ways. You can also have arguments to reorder the arguments for things like internationalization, if the order needs to be different. So as I mentioned, the for loop is based on iterators, and so you can also, iterators are nice in that they don't require any extra allocation, and also in that they're very easy to chain together. So here, instead of having the final case of the match statement, the catch-all kind of default case, instead of having it do nothing, here I'm having it actually fail. And then instead, in the actual iteration, I'm filtering out all the spaces instead. And you can see this, it's still, it calculates the value here. Another thing to note here is that the filter method takes closure as an argument. Closure syntax is based on Ruby's block syntax. This closure takes each character in turn, and then you can do, you just filter it out. It's basically like grep. The ampersand there is a pointer thing that we'll get into in a little bit. You can also note that the closure doesn't actually require a return statement. Just like in Perl, the return statement at the end of any function is optional. And yeah, that's that. So in addition to basic types like integers, floating point values, arrays, things like that, Rust can also build more complicated data structures using structs. And so this right here is declaring a point struct. It has x and a y, they're both integers, and you can print it out. You print out the x and the y components, and that's what you get. structs are required to be allocated or initialized, just like all other variables. You can't have uninitialized data. The structs are also entirely memory compatible with C, so you can pass them back and forth between C and Rust. That's one of the big things that Rust is trying to do, is be as compatible with C as possible in order to be able to interoperate with existing libraries and that sort of thing. So you don't have to convert all at once. Rust also has enum types, basically just a list of potential values that the type can hold, just like C. Oops. Like here, you have a color enum, which has red, green, and blue as potential colors you could use. And here, if you declare a variable with a value of red, you can print out, you can do a pattern match on it. Rust, like I said, guarantees that the pattern match has to be exhaustive. It has to cover all of the possible values that the type could have. If you have, say, if you don't cover one of them, you get a compiler error. Here you can see it says non-exhaustive pattern. You didn't cover blue. It tells you what you're missing. It's useful when you're doing things like refactoring, just to make sure you don't miss anything. And if you have an extra case, you can see it's saying that expected a color, but it found an integer. You'd have some random other thing in the match case, and it just tells you that you're doing something wrong there. The nice thing about Rust enums, though, is that they're actually, if you're familiar with algebraic data types from things like Haskell or OCaml or things like that, you can attach data to the enum values. So here I added a custom color type, which takes 3 values, 3 integers, and here you can print. Here I have the match statement now. It includes the custom color and prints out the values for the color, and then red, green, and blue are hard coded in there. And so you can see how those kind of things are also handled. You can see how in the match statement here, when you have an enum value that includes data like this, it's actually binding the values to the R, G, and B variables. It's creating new variables called the structuring bind, if you're familiar with the concept. And you can use that both in match statements and in variable declarations. The Rust standard library includes a lot of useful examples of enums. It has an option type, which looks like this. That should be pretty familiar if you've used things like Scala or Haskell or OCaml and that sort of thing. Basically, just allows you to have a variable that might have a value or it might not. Basically, instead of like in Perl, you have undef. In Rust, everything has to be defined, but if you need something that might have not a value for whatever that might mean, you can use the option type instead. And this will make sure that you actually handle the case of it potentially being not defined, rather than just having random things happen. This is also a good example of Rust support for generics. You can see the option type has a type parameter there, t, and you can see that the sum variant of the enum takes an argument of type t, and so you can use options for any data type. That's what that means. And so as you can see from these examples that I've been giving, Rust is also capable of type inference. You pretty much never have to actually declare the type of variables that you define. It doesn't do type inference for function signatures, and that's pretty much because they want to make sure that for actual API, actual public API, that you are explicit about that, so that you make sure that your public API doesn't actually accidentally change by you just changing something that adjusts the type signature. So in addition to the basic built-in types like integers and floating point values and things like that, Rust also has a standard library with a bunch of useful types. Here's an example of vector, which is basically the same. It's approximately equivalent to vectors in C++, if you're familiar with that. It's just a list of values that you can potentially it's potentially growable, so you can add new things to it. Here, declaring an initial vector with 6, 8, and 22, and then pushing another number onto it. And you can print out the length, and you can print out, you can iterate over the values, print them out. And see here, you prints out the length and the values. There's also strings. You can modify them and print out. They also have methods like that. Something to note is that both of these examples use special initialization for the variables. Here you have string from str, and then from in the vector example you had the special vec macro there. That's because the default, the basic type of say a string literal there, or an array in Rust is a fixed size, and so if you want something that's capable of growing, it needs to be able to allocate its memory elsewhere, and this is just how you declare a variable that's of the type that's capable of growing, basically. Another thing that you can see here is that I'm calling methods on these variables. Rust allows you to define methods by defining implementations of a type. So here we have the point example that I showed you earlier, and here I define an implementation. The impl keyword, implementation of the point. I define a couple methods on it. Here, you can see the new function there is a static function because it doesn't have a self parameter. The x and the y methods are actually instance methods because they do take a self parameter, and then you can create a new point by calling the point new function, and then print out the different values by calling those methods that I just created, and that works the same way as the original one did. These methods are all using static dispatch. Dynamic dispatch is possible in Rust. It does exist, but it's a bit more complicated and not really in the scope of this talk. But if you need it, it is there. One final aspect to the type system is that Rust does have traits, pretty similar to traits in other languages. You declare a trait. Here's a trait area at the top, which defines that it requires you to implement a function called area. And so you can implement area for the rectangle struct and implement area for the circle struct, the different implementations there, and then you can just calculate the area in a generic way and see in the print area function. The other thing you can do with traits is use them as bounds on generic types. And so here the print area function takes any type T as long as it implements the area trait. And since you know that it implements the area trait, now you can call the area method on it when you're printing out the area. And here it just prints out the area of a circle and the area of a rectangle. And then you can see what the values are. Traits are also used by the language and the standard library to represent various different properties of types. There's a trait for being able to convert it into a string. There's a trait for being able to test for equality. There's a trait for most other operator overloading kind of things. Those are all handled through traits, and so you can implement these specific traits on your new types that you create. And so this isn't the details of this example here aren't really important, but this is just showing that I can implement the show trait, and then once I do that, the empty curly braces in print line can just print out an instance of a point on its own without having to handle the components separately. So something that has come up a couple times here is the ampersand in front of the types. This is Rust has a couple different types of pointers. You might have heard that Rust has a lot of different kind of pointers, and it's really confusing and everything. They've done a lot of work in the past couple of months to really simplify that. It's really not that bad right now. In general, most of the values that you'll be dealing with are just values they allocated on the stack. So they're not. They don't have pointers at all. You're just dealing with the value itself. And this is true for both built-in data structures like integers and also for more complicated data structures like structs and enums and that sort of thing. And this is good because it's really fast, but it also has limitations in that it requires a lot of copying because allocating values on the stack like this these values are only valid within the function that they're declared in. You can't if you want to call a function with one of those values, you have to copy it into the function. If you want to return it, you have to copy it back. And this is not normally a problem for small data like integers, but for bigger data, doing all that copying is not always a great idea. And this is why you end up passing pointers around. So in Rust, the kind of pointer that you'll probably be running into most often is called a borrowed pointer. What this does is it takes a variable that you've declared. The compiler verifies that when you take this borrowed pointer, the pointer itself cannot live any longer than the variable itself lives. If you try and do that, you'll get a compile time error. And so this solves the problem that you run into in C and C++. Like here, you declare a variable and then return it on a stack, and you return a pointer to it. The issue here is that once the function foo returns, that pointer gets deallocated, and it no longer points to anything meaningful. And so this is something that'll compile just fine in C++, and it'll just cause nonsense or seg faults, or probably not seg faults, but just give you bad data at runtime. So if you try and do the same thing in Rust here, where you declare a variable on the stack and you return a pointer to it, you actually get a compile time error, where it says right here, the variable x does not live long enough because it only lives for the scope of that function, and then you're trying to return a pointer to it that will live longer than that. So in order to deal with a situation like this, where you actually need something to live longer than that, there's another kind of, you basically need to allocate a new chunk of memory that will live long enough. In order to do this, Rust will allow you to explicitly, they call it box variables, which is just to allocate a new chunk of memory for the variable, and then use the data in this. So here we have the function is now returning a boxed integer, and you declare box variables by just the box keyword, and then you can return this and this, and then return the pointer and then dereference it, and this works fine. Here it just prints out the value, and that works fine. This is not usually how. Okay, so something that you also should notice is that there's no explicit deallocation code here. This isn't actually leaking memory. The compiler can actually trace through the code and figure out where the data is no longer being used, and it automatically inserts the appropriate deallocation code without requiring anything like a garbage collector or something to kind of clean up after it. The way that it does this is through a concept called ownership. And this basically means that only one variable can be holding that pointer at any given time. So if you try and declare a boxed pointer here, and then you try to assign it to two different variables. Oops. Here you get an error because you're trying to use the moved value after it's already been moved. So when you do an assignment from a boxed variable, it doesn't actually copy anything. It does what's called a move. And what that means is that all you're doing is changing which variable can be used to refer to the same memory. And so if you try and do that twice, like once you get to the line that you're trying to assign to Z there, X is no longer a valid variable to use at that point, and so you get a compiler error. And with this restriction, the compiler can easily check and see where the variable is no longer being used and insert the appropriate code to free the memory. So boxed variables aren't usually used in this kind of code. It's not usually necessary. What they're actually more useful for is in building data structures. So if you, for example, are trying to create a list data structure like this actually doesn't work because this is the type is referring to itself. It's a recursive type, and so it doesn't actually know how big the type has to be because the type contains itself. And so you can see the error message here says that you should, it's an illegal recursive enum type, and you should wrap the inner value in a box in order to make it representable. And since boxes are always the same size, they're just a pointer. It can figure out how big the type needs to be, and then everything works. And so you can see here, I changed it to a boxed pointer at the end there, and then this will run fine. This also shows an example of a special format for println, which works basically along the same lines as data dumper. It uses reflection to actually go through the data type that doesn't actually have any toString or anything like that defined for it, just any arbitrary data type, and goes through and figures out just some way to represent it so that you can, it's for debugging mostly. And there's so other than borrowed pointers and box pointers, there's also unsafe pointers or raw pointers, which are pretty much only used for interoperability with C, and you can pretty much ignore their existence. They're not unless you're writing like C bindings. They're not used in normal Rust code. Something to note here is that when you're using borrowed pointers and box values and things like that, the pointers always have to be initialized. Rust doesn't actually have the concept of null. You can't create a null pointer like this. You can, if you need like a pointer that might or might not exist, you can use the option type. And Rust actually, the compiler actually knows that pointers can't be null, and that the option type has like one extra value that doesn't that isn't a valid value, valid pointer value, and so it can optimize optional pointers down to just a normal nullable pointer in terms of the code that's generated. So this is another example of the zero cost abstractions that I was talking about. You don't actually need to use any more memory to represent pointers, even though you're using like an option in that sense. One last thing that I wanted to talk about is that Rust has put a lot of effort into concurrency. Rust's concurrency is based on tasks, which can be, it defaults to having tasks that map one-to-one with OS level threads, but they also have an end-to-end scheduler if you need that as well. The Rust compiler actually uses the same kind of ownership semantics that I was talking about that it uses to ensure memory safety in order to ensure that there are no data races when accessing the same memory from multiple tasks. So the basic idea behind that is that Rust all data races are caused by data that's both mutable and aliasable at the same time, meaning that it can be modified and multiple things can be modifying it at once. So any memory that's shared between tasks has to either be entirely immutable, or the task that's modifying it has to be the only one that's capable of modifying it at that point. And so here's an example of a program that spawns a new task, does something that takes a lot of time in the task, and in the main task, it then waits for a result and then prints it out. You can see here the channel function here just sets up a basic communication channel. It's basically equivalent to the pipe keyword in Perl, except it's an internal thing. It's not actually using OS level pipes. I don't think it might be. And then spawns a new task. The proc here is a special keyword. It's a special type of closure. Normally, when a closure in Rust closes over variables in the environment, it takes borrowed pointers to the things it closes over. Proc takes owned pointers to the things it closes over. And so after it closes over variables, it takes owned pointers to mutable things that it closes over. And so once it closes over variables, you can no longer access it in the main thread. And so here, the proc is closing over the right end of the pipe. And so if you tried to access the writer end of the pipe of the channel in the main thread, you'd get a compiler error because only one thing can be writing at the same time. And the same thing here, the main thread is trying to read from the pipe, and if you try to read from it in the subthread or in any other subthread that you spawn in this way, you get an error. And so you know that only one thing can be writing and reading from the pipe at once. You can also see that it is closing over the m and the n variables. but that's okay because they're just immutable data, and so you can use them both in the main task down here and in the subtask up there, and that's fine because that's just immutable data, and that's not actually going to cause a problem. And so you can see this running here. It calculates and then prints out the value. And so that's kind of most of the main features that Rust has. Rust also has other things, like it has namespacing in the module system. It has privacy controls. It has integrated testing and benchmarks, which are pretty cool. You can write your tests in line with your code and have them executed by the compiler with special flags. The compiler itself has a lot of they call it lint checks, which are basically extra warnings that you can add. You can make them individually into errors or ignored or whatever, for things from basic like style issues to disabling large parts of the language that you might want to ensure that your product doesn't use, like allocation if you're writing like an embedded system, things like that. The entire runtime, like I said, can be left out or re-implemented in a simpler way in order to support being run on systems where getting the entire runtime up and running isn't always possible. There's already existing projects that can run to write a kernel in Rust, like an operating system kernel in Rust, and to run Rust code on like an Arduino, things like that. That's already working. Rust has a powerful macro system available to user space code, to user code. It's powerful enough to implement a lot of really useful things. Anything you see here, like that ends with an exclamation mark, is a macro, and the macros always show up in this form where it's an identifier, an exclamation mark, and then balanced parentheses of some kind. So external tools are still able to parse the overall code, which is a useful property to have. And the language itself is also very flexible on its own. Most of the language features are implemented via normal Rust functions, either through traits, like I mentioned earlier, for things like operator overloading on custom types, or via they call it language items for low-level operations like allocating memory and handling failure and that sort of thing. And so it's very flexible, and you can implement however you really need to get it to run wherever it needs to run. So if you're interested in learning more about Rust, here's a bunch of useful websites. A good start for the language, there's a tutorial on the Rust website. There's also a Rust in 30 minutes, kind of an overview of the basic concepts, just to get an idea of what the language is like. They have a web-based REPL on play.rustlang.org, and Rust by Example has a lot of has a lot of useful examples that you can run in the REPL to see how different parts of the language work. If you're interested in getting into Rust development, it's developed entirely openly. It's very welcoming of new contributors. Discussion happens on IRC, on the Rust channel on Mozilla's IRC network. There's a Rust dev mailing list, and Mozilla, the Rust team in Mozilla Research has all their meetings openly every week. For making actual decisions about where the language is going. For keeping up with the language itself, this blog.octane.net has a series of This Week in Rust posts, which just keeps you updated on things that might have changed in the past week. It's still that's kind of slowing down these days, but there's still are things that are changing, and so that's a good way to keep up with that if you're not actually following the community regularly. And this last, in terms of getting involved in development, the GitHub wiki has a whole list of things to know about when you're getting involved. Rust has a community standards of conduct that is very well enforced by the Rust team, and that, in my experience, has made the Rust community one of the most friendly and pleasant programming communities I've seen. And so if anything here sounded interesting to you, I highly recommend getting involved. So yeah, any questions? Yeah. Yep.
I did have a question about the ACK function or the...
Yeah.
How is it returning a value? I mean, I see it declares that it returns a uint, but...
Yeah, so it's the same as in Perl. Everything you don't actually have to return. Yeah. And Rust is also an expression-based language. So all the control structures are also expressions, and so the match just returns whatever it
ends up with that.
Yeah.
What sort of features do traits provide? Are they close to moose rolls, or are they closer to interfaces?
So yeah, they're pretty close to Moose roles-ish. I mean, they're more than interfaces in that you can do things like have default implementations. You can't. I don't believe you can have data associated with them, but yeah, they're kind of halfway in between. Yeah. Anything else? All right. Thanks.
So